Okay, so let's start again. Today our first speaker is Yannis from body technique, and he'll tell us all about experiments with terahertz spectroscopy.
Thanks, Mike. And thanks to the organizer for the kind invitation to talk at this workshop, which is very inspiring and stimulating, trying to connect different communities. So I'm an experimentalist. I will show you mostly experiment, a bit of modeling, okay? I would like to discuss some non-local and temporarily engineered terrestrial material interaction in surface plasmon cavities. So let me give you a little bit of the context and the motivation for this work. So what we do is we fabricate and we study with terrestrial light this kind of structures. So these structures, they are, let's say, a single unit that here has a plasmonic cavity. So a cavity, a trap for photons, operating the terrestrial frequency range, and this cavity uses a plasmonic mechanism for light confinement. And these cavities, they are arranged in a periodic array, as you see here, and they realize the so-called metamaterial. We do this for two purposes. First, the metamaterial aspect. So what you see here, in some sense, is an artificial crystal for photons that we can design in order to engineer and manipulate properties, the properties of the charged photons in ways that natural crystals do not necessarily provide in this frequency range. In particular, we like this platform. So there are different taking cavities in the terrestrial range. These plasmonic cavities, the nice assets is that they are very tunable with different parameters. I will show a few during this talk. And so we use this in order to functionalize basically the cavities. And more generally, we use this to engineer charged light material interaction. The second purpose, which I will not touch upon during this talk, is the fact that because they operate at terahertz frequencies, actually terahertz frequency range, there are many collective modes of quantum material. We have heard about this during this workshop. And so there have been in the past years many theoretical proposals and the first few experiments showing the promise of putting quantum material in very, very small cavities to achieve ultra-strong light-matter coupling with some of these collective modes that would enable to manipulate the macroscopic properties of this quantum material when you put this collective mode under ultra-strong coupling. So for this, the cavity needs to be ultra small, and this is what we do with this metasimplicity. Okay, so in the context of this workshop, I would like to discuss two aspects of the physics of this metamaterial, a phenomenon that appears near equilibrium, which corresponds to the non-local interaction between terahertz photons and the electron gas, which is making up this plasmonic medium, which is underneath here. And the second aspect I would like to discuss is a far from equilibrium, actually very far from equilibrium phenomenon in which we strongly drive the system periodically to, let's say, engineer functional properties now from a temporal approach rather than the spatial approach that you see here. So this is a spatial approach for engineering your structure spatially. And in this experiment, so we realized some recent concept that appeared in photonics, which is called photonic time crystal that I will introduce. We do this from a temporal approach. Okay, so the way I organize the talk is as follows. I will start, it's a bit peculiar, so I will start right now by motivating or introducing first the photonic time crystal and motivating why it's interesting to realize this system and why it's actually challenging experimentally. Before presenting the result, actually, I will make a detour, actually, because I need to present this metamaterials, these plasmonic metamaterials, and it's easier in equilibrium or near equilibrium. So I will use this opportunity to discuss this non-local light material interaction that we found out in the system. Okay, so feel free to interrupt me anytime. So photonic time crystal. So this is, as I mentioned, a recent concept that emerged in the last few years. So these are like optical systems which are strongly and periodically driven, modulated in time. Okay, and they can be understood as a temporal analog of a more regular spatial photonic crystal, okay, that you may know. But let me recall what is a spatial photonic crystal. So you take, let's say, a piece of glass, okay, with a given index of refraction. And so let's assume it's frequency independent. So the photonic band structure looks like this. So the photonic dispersion, frequency, momentum, okay, it's just lines like this. So spatial photonic crystal, there are systems in which you periodically modulate in space, okay? You put a dielectric contrast on wavelength scale. So you structure a system like this with a refractive index, which is modulated in space. And if you do this, you will create replicas of this photonic band structure, which are shifted along the momentum axis. Okay, so these replicas, I will cross the original dispersion at this point here, and eventually there will be the opening of a gap, via coupling. So this gap is a frequency gap, okay? And this frequency gap is, let's say, is kind of a discovery in the mid-80s with the spatial photonic crystal. So what is shown as a solid line here are the propagating mode in the system, okay? So now if you want to know what's going on inside the gap, what you can do is you take a certain frequency which is within your gap, so a real frequency. So you have a wave, typically you use this plane wave, for example, of this type, okay? And you solve your wave equation. So in the context I will be talking here, these are Maxwell equations, but this also works for any type of other wave system, acoustic waves. Okay, so if you take a real frequency and try to find the solution to your wave equation within this gap, you will find out that the momentum, the wave vector here, acquires an imaginary part, either positive or negative. These are just the solution to the wave equation. So it means that the amplitude of the wave now in space as a function of spatial coordinates is either decreasing or increasing, okay? But we are in equilibrium, so typically we discard the growing solution because it's unphysical. It will mean that the energy goes up to infinity. The system must conserve energy. We are in equilibrium, so we discard this solution. So the only solution that is physical is the one that decays in space, and this tells you that the wave will just decay in space. So if you now put an atom, for example, in this spatial photonic crystal, the wave decay, it will not emit light, okay? So this is one of the major discoveries in the mid-80s, this inhibition of spontaneous emission in spatial photonic crystal by Javier and John. And so since then, it has been really a central concept in order to engineer light matter interaction in solid state systems. So typically you can enhance or inhibit spontaneous emission. Here you have small or zero group velocity. This is the derivative of this curve. So you have slow light effect. You can enhance nonlinearities. And if you create a defect in your photonic time crystal, in your photonic space crystal, sorry, like this, you have basically Fabry-Perot cavities in which you can put emitters, in which you can put excitons, anything you want, and realize basically a Fabry-Perot cavity. Okay, so lately, there have been the concept of photonic time crystal emerge. Now let's assume you can do the same in space. So you can modulate periodically, in time. You can modulate periodically in time the refractive index quite strongly. You can understand what's going on thanks to the duality between space and time in Maxwell equation. You have to take care, of course, of causality. But with this analogy, you can understand what's happening by exchanging space and time on the one hand and momentum and frequency on the other hand. So if you do this, you will have also replica of your original band structure here, which are shifted now along the frequency axis, okay, not the momentum axis. They will cross again the original dispersion here. They will open a gap, but because you have exchange space and time, momentum and frequency, basically now the gap is a momentum gap. Okay, and you can do the same. You can wonder, okay, what's happening within this gap? So I take a real momentum and I solve my wave equation. And conversely, you will have that now the frequency acquires an imaginary part. Okay, so that tells you that the amplitude of the wave now in time is either decreasing as a function of time or increasing. These are your two solutions. But now you're in an out of equilibrium system, so this solution is physical. You can keep it because the wave can take energy from the modulation. Okay, you are in an out of equilibrium system. So that leads to the prediction that inside these momentum gaps in photonic time crystal, the wave can grow exponentially. So if you put now an atom inside this photonic time crystal, it will start to emit, the wave will be amplified, you will get parametric amplification and lasing. So this prediction is what kind of kick-started this field a few years ago. And since then, from mostly a theoretical perspective, the field is booming and people are exploring what kind of new thing you can realize with this, or how the light matter interaction actually modified compared to equilibrium systems. So this is, if you're interested, a review on the topic. And these are a few key aspects. So really the list is not exhaustive here. So prediction of amplification and lasing. More generally, this is, you're doing nonlinear optic in some extreme regime of parameter. So this may allow for light generation and conversion, typically with relaxed phase matching constraints. You can overcome some bounds that you find in electromagnetism, which are only valid in equilibrium, because now you are out of equilibrium. And in terms of light matter interaction, this gives rise to novel form, let's say, of light matter interaction in the system. So one I show here, for example, is what these authors call spontaneous emission excitation. So the atom is in the ground state, it jumps to the excited state, and then it emits a photon. Okay. Yes.
So, I mean, if I think about this like usual kind of parametric resonance,
yep,
then ultimately, I guess it's nonlinearities or dissipation that limit, you know, the exponential growth.
Exactly.
In these systems, is it, I mean, what happens as the amplitude keeps growing?
So theoretically, it grows to infinity.
Right.
In experiment, this is what makes it challenging to realize, because you need to drive the system very strongly and you will likely have limitations. So it can be, let's say, you need a nonlinearity in your system, but when you drive it too much, this nonlinearity will have other types of nonlinearities which typically will limit. And so experimentally, we are starting to explore this system, so it's not clear where is the limit. And so, but clearly, as I will mention just after, these are really strongly driven system, and so you can expect all sorts of things. I will mention one, which is typically heating of the electron gas. You have the question? Okay, so an important point here, so that you don't get confused. So it's a disclaimer, because you have heard maybe the wording like time crystal in the scientific literature. So now there are two types of time crystal. Okay, there is the time crystal which originally, let's say, so many body time. I will call them many body time crystal. Okay, quantum many body time crystal. These originate from the original proposal of Frank Wilczek, which says that the systems can break spontaneously time translational symmetry, either spontaneous in the original proposal and later on discrete. So in that sense, you would have, for example, frequency you drive at some period and you will have frequency doubling. These are not the type of time crystal I'm talking about. Okay, so the one I'm talking about are called photonic time crystal. They are just the temporal analog. They may break this time translational symmetry, but they don't do it necessarily. So if we drive the system at a certain frequency, the system oscillates at this frequency. Okay, so don't get confused because the wording is really confusing. Call them, if you want, temporal photonic crystal. Okay, so what do you need to do actually to realize a photonic time crystal? You need yes.
The distinction is that it's not spontaneously broken.
Yeah, it's not spontaneously broken. It's just driven at the same frequency. Yeah. So what do you need to do to achieve a photonic time crystal? You need to fulfill two conditions. Okay, you need to have very strong and periodic modulation of the optical properties. So when we say very strong, it's very strong because, for example, if you take the refractive index, you would like it to modulate on the order of 100%. Okay, in analogy with a spatial photonic crystal, where you have a very large dielectric contrast of your refractive index, spatially structured typically between 2, 1, 2, 1. Okay. Why is this requirement important? Because you want to open a gap, okay? And the size of the gap will depend on the strength of the modulation. So if you make the modulation too small, the gap will maybe open, but with dissipation, you will not see it, okay? So typically, this also tells you that this kind of nonlinear optics phenomena happens in a non-perturbative regime of light-matter interaction. So we'll use typically Floquet theories to describe this. And another important aspect is that the modulation needs to be ultra fast on the time scale typically of the light you are considering. Okay, so you want to open the gap at this particular frequency. Typically, you will need to drive, for this to happen, you will need to drive the system at this frequency or twice this frequency. So it needs to be both ultra strong and ultra fast modulation. Okay, this is what makes it difficult to realize experimentally. In that respect, here there have been other type of photonic media that have emerged that are time modulated, but typically the frequency of the modulation is very small compared to the frequency that you consider. So you will take, for example, a ring, a transparent ring in which light can propagate, and you will modulate this with a, let's say, electro-optic modulator at a very low frequency, typically kilohertz, megahertz. So the frequency of the light is very large compared to the modulation. You can do very interesting thing with this. You can, for example, create sidebands. So you can create a discrete lattice and use this as a synthetic dimension, okay, for example, for controlling the photonic properties. But what happens is in photonic type crystal is really qualitatively different because you have this moment and gap opening and amplification and nasing, okay, that you don't have in this regime of parameters. Okay, so this photonic type crystal, they were originally, let's say, explored in the optical frequency range. And so far, there have not been any experimental realization. Yes?
Can I ask a short question?
Yes.
On that point? Maybe it's just a question.
Sure, sure.
You say it's really hard to drive the system at the same frequency as light, but why not use light to drive the system?
Yes, you will use light to drive the system.
Then it's almost trivial.
Yes, but you need to make it very strongly and very fast. So let's say, what I'm going to say here is that not all material respond very strongly and very fast. So very strong means really you need to modulate your refractive index by an order of 1. The relative modulation needs to be order of 1. So you really need to change the refractive index between 1 and 2, 1 and 2. And the system needs to respond also on the time scale of the light.
It's the response that needs to be on that time scale.
Yes.
Yes.
So indeed, in let's say you can always find material that fulfill, let's say, one of the two conditions at optical frequencies. So the way, I mean, typically you take a non-linear dielectric in which people have done nonlinear optics. So we convert red light to blue light. So this system, typically you will have ultra fast modulation. Otherwise you wouldn't have the conversion of the light. From red to blue, but typically the modulation are rather weak. Okay, they are below %. And on the other hand, you have material which respond extremely strongly. These are like plasmonic material. Sometimes often they are called like ENZ, epsilon near zero material, like ITO, let's say indium tin oxide. So they respond very strongly. The refractive index can be modulated of the order of 100%. Problem is that they respond slowly. Okay, so they follow the amplitude of the optical pulse that try to drive them, and they do not follow the cycle of the pulse. Here we want really to have this ultra fast modulation that follow that are field driven. Okay, so far the
and you don't want to work like near phonon frequencies because that's just wavelengths are too short then.
In principle, this concept applies everywhere. So you can work near phonon frequency. You can try to drive a phonon to modulate material properties.
Right.
If you're
that both of these things though, I mean, doesn't it have everything you want? If you were to work near a phonon, drive a phonon.
Yes. So one needs to see then if your phonon is able to modulate optical properties very strongly. That's the thing. So you shake your phonons. What kind of modulation, let's say, of the refractive index?
Raman phonon. I see. Okay. But maybe the wavelength is not long enough. Is that also an issue? You want to do something bigger with a longer wavelength, or you don't care?
No, not necessarily. Not necessarily. You just need to drive the system, and the change of the optical properties need to be really large. Okay, so if your phonon can give that, then for sure.
So you couldn't work with a material that is essentially inversion symmetry breaking.
Mhm.
So you mix Raman and optical modes, and then drive what is ostensibly a Raman mode, which modulates the dielectric constant,
Yeah.
but through the IR dipole.
You could do that.
Okay.
Yeah. Now the question is the strength.
Oh, I see. It's not. Oh, okay. I would guess
That's the strength.
on resonance would be as strong as you could ever want, but it's not true. You're saying.
Yeah, at some point you're gonna typically. So here I mentioned, okay, so if you have weak modulation, then you will crank up the field. At some point you may reach like damage threshold of your material. That's the thing. Because really to modulate the refractive index by the order of 1, you really need to pump it hard.
Also, if you're at resonance, don't you have maximum dissipation?
That's also the tricky part. The material will absorb a lot, and then again you will certainly arrive also the damage risk. Okay, so far the experimental realization are more like analog with electrical circuits. Okay, because here you can modulate the capacitance and the inductance with nonlinear components pretty straightforwardly. And so people have seen this physics I'm talking about, okay? And but an all optical realization was not made until we done it, at least we claim, in this plasmonic material that I talked about at the beginning. So this is realized at terrestrial frequencies, okay? So above the microwave range, much below. So we are talking about terrestrial light, so milli-eV photon energy. So much below this optical range. Yeah, in this plasmonic material is done all optically. Okay? So we really modulate the optical properties of this plasmonic metal surface. Okay, so now let's go back to near equilibrium. I make the detour. I present to you this platform.
So in this metamaterial, what is the actual material that it's
So this is what I'm going to explain. Now I'm going to introduce this metamaterial, and I'm going to go back to near equilibrium before presenting you the results. Okay, so this metamaterial is, so we have a plasmonic material here. I will introduce. So it's just a solid state material. It's a Drude gas. Okay, it's an electron gas which for a Drude model at terrestrial frequencies, and we structure this system. I will explain in a second with dielectric and metal on top, and it's periodic structure like this. So this is our plasmonic material. So which is at the bottom. It's a semiconductor which has a very low number of electrons. And so the plasma frequency is very small. It's in the terrestrial frequency range. Okay, so what you see here is a reflectivity as a function of frequency. You may recognize the typical plasma edge you see in Drude metals. In Drude metals, this happens typically in the optical range. If you take gold, silver, so this will be at much higher frequency. But it has basically you can fit this perfectly with a textbook Drude model. Okay, so in terms of the bulk material, let's say the material is opaque to bulk wave, so it doesn't let the bulk wave propagate through it. Okay, that's why the material is reflecting. That's why we see ourselves in a silver mirror typically. And above the plasma frequency, which is here at 2 terahertz, it becomes transparent to bulk wave propagation. Okay, so the material becomes transparent.
Yannis?
Yes.
Sorry, can you say why the plasma frequency is so low? Is it because the density is low?
The density is very low. So we are at like 10 to the 16 carriers per centimeter cube.
Okay, and to give me a reference for gold or
to the 21, to the 22, yeah.
So this is a semiconductor?
Yeah, this is a semiconductor. This is a 3-5 semiconductor. If you want like gallium arsenide.
So then I guess all these things are then kind of temperature tunable as well?
Yes, exactly.
Okay.
So that will be the part of the experiment I'm going to describe. It's tunable. Okay, so this is the bulk system. Now, how do we make our surface plasmon cavities from this? So I just go back to plasmonic for a second. How does it work? So this is the dispersion relation of the wave inside the system as a function of the parallel momentum along the interface between the plasmonic medium and let's say vacuum. Okay, so again, here this is transparent for bulk wave, but this is opaque for bulk wave. So bulk wave cannot propagate, but then you have this surface mode, which are the surface plasmon, which disperse in a very peculiar way. So you have frequency momentum along the interface. Okay, so they start by following the light line, which is just the dispersion of the light in vacuum here, and they bend. Okay, that tells you that you can have extremely high momentum at finite frequencies. Okay, very different from photons in free space, in which if you want very high momentum or very small length scale, you need to crank up the frequency. Here it saturates below the plasma frequency. So it only works, this mechanism, if you really want to confine the field, so it works both along the interface, okay, for the K parallel, but also at the same time it squeezes across the interface. So it's really squeeze the photons to very small mode volumes, okay, when you go in this area. So yes, so if we want to do this at terrestrial frequencies, the point is that we have to use a material that has a plasma frequency at the terrestrial frequencies. If we were to take gold, here, I mean, the plasma frequency will be so high that will be on the light line at terrestrial frequency, so we will be not confined. So sometimes you see, let's say, metamaterial, terrestrial metamaterial made of gold, which are called plasmonic. Strictly speaking, it's not. Okay, the plasmonic mechanism is really the one that works when you have a plasma frequency in the terrestrial range. Okay? So the way now we build our metamaterial, so out of this excitation, so we're just gonna put boundary condition to this mode. To make a cavity. So we have our plasmonic material here. We put a dielectric so that the photon can propagate. We put gold to basically confine the field in this direction. And here you have boundary condition. So when we shine terrestrial photons, they by near field, they couple here. You can see this, if you want, as a waveguide for photon with boundary condition. So they bounce back and forth and there is a resonance appearing. So these are like periodic arrays, let's say, of sub-wavelength Fabry-Perot cavities. Okay, the thickness here is very small compared to the terrestrial wavelength. And in some way, the way we tune the resonance, we can tune it geometrically to start with. So we take it's a little bit more complicated than this, but I simplify. So you have the surface plasmon dispersion relation. You just like put a stripe of gold of, let's say, width S. And this gives you a momentum here, and you look on your dispersion relation, and you have the frequency of your cavity. Just put boundary condition. Okay. Yeah. Okay, so this is the bulk plasmonic material. So reflectivity as a function of frequency, as I showed you before in experiment and simulation. And now, so when we structure our material, okay, we see this. So we see very strong absorption, different absorption. Okay, so now when this is structured, and because it matches pretty well with simulation, then we can ask us the simulation. So what is the mode here? So for example, this mode that resonates here is basically what you see here is that the photon get trapped inside this resonator. Here this is a magnetic field out of plane. So what you see here is a half wavelength, the fundamental mode of a Fabry-Perot resonator. Okay. Then you have this mode, which is a third mode, and you have another mode here, very close to the plasma frequency, which is located between these cavities. We call it the intercavity mode. It's also a resonator for surface plasmon. They just have a different symmetry. Okay. I will mostly focus on this mode for the rest of the talk. Okay. Remember these two modes because now we'll show you some color maps. Okay. These two strong absorption, this one and this one. So as you mentioned before, the nice thing of this material is that
just to get it was going a little fast for me there. Just to understand. So we're here in these pictures on the right, we're looking down along these wires.
Yes,
right?
we make a cut here. So we make a cut here, and I show the magnetic field pointing out of plane here. So the electric field, if the magnetic field like this, the electric field is positive here.
This little yellow
in the middle.
Little yellow line is one of these. It's like
yes, it's the goal. It's the goal. Yeah.
Okay.
Sorry. Yeah.
I'm seeing one unit cell.
Yes, exactly. Exactly. Yeah.
And then so is there? Those are all the lowest modes, or there's different? There are modes in between as well. So you say third, but there's no second, or you just didn't show it?
No, second, okay, we do the experiment at normal incidence. Second is forbidden by symmetry. It's a hot mode. It's a little bit like Raman versus dipole active. So at normal incidence here, the second mode actually doesn't carry any dipole, so we don't excite it. If you do this at 45, you will excite it. Yeah.
And so this thing has two nodes. So there's these maximums of intensity there.
Yeah,
in the third cavity
field.
mode.
Yeah.
Like say in the third one, there's this maximums intensity, and I guess trying to understand. I'm a little surprised that that's not weaker in this plot than the others. So you kind of are coupling and making these regions of high intensity, but they're more or less all the same. I just see bright red, and I just would think the middle one is weak.
Yeah. Yeah, it's weak in spectroscopy, but you can extract it here. For example, you can, okay, it's a little bit complicated, the simulation. These are like when you remove the damping, for example. Okay, so it's just to highlight the mode. It's true that its activity optically is really small. Yeah. So it's like you put an imaginary part to the mode, a positive one to kind of damp all the other mode to just select this one to show it. Yeah.
And they correspond also in terms of frequency in 1, 2, and 3. So this intercavity mode is the highest one.
Yeah, exactly. This is the one very close to the plasma frequency.
Maybe then to conclude, there will be higher modes also if you would go to higher frequency, right? I mean, there seems to be another maximum at the end of your
oh, okay. So this guy is actually a diffraction mode. Okay. So now above the plasma frequency, remember that the plasmonic medium is transparent. So now you have a grating on top of a transparent medium. It will act like a grating. It's just that this grating mode is actually forbidden to live here because the material is not transparent, but above is allowed. So it just appears above the plasma frequency. That's okay. Okay, so as you pointed out, so the nice thing is that this bulk plasma frequency is actually tunable with different parameters, and one of them is the temperature. And the way it happens is that this material has a small band gap. So as a function of temperature, you have thermal activation of the carrier. The carrier concentration changed, so the bulk plasma frequency changed. And you can really tune it between, let's say, 2.5 and 0.5, in between 200K and 300K. Okay, so we are tuning this parameter, which tunes this parameter. Now, what happens for the structured system? So this is, again, just the bulk. You recognize the two major modes we saw before. So the cavity mode here and the intercavity mode here, which is very close to the plasma frequency. And here I report, so this is now as a function of temperature on the right axis, which correspond to given bulk plasma frequency here, okay? So you see that when you decrease the temperature, so you decrease the plasma frequency, these two modes, they just follow, okay? So they just decrease, okay? This is the frequency here as a function of the temperature. Okay, this tells you two things. This tells you, okay, the material is tunable. You can tune the resonance of your cavity with temperatures. Second thing is that you see that the cavity modes, whether it's the cavity mode or intercavity mode, they remain bounded by the plasma frequency. And this makes sense because these are surface plasmons only allowed to exist below the bulk plasma frequency. So if you tune it down, they just follow. Okay, so this gives you a mechanism for tunability. Okay, so two things. So surface plasmons support the cavity resonance, and they just remain bounded by it. If they remain bounded, it also means that what you see as a function of temperature, because we are not changing the geometry, so we are not changing the photon box. Okay, but the wavelength of the resonating photon actually increase because the resonance frequency decrease. So that means effectively as a function of temperature, we are increasing the confinement, okay, of the photon. The size of the photon has changed, but the resonating frequency when they increase the temperature is actually increased. So one way actually to see this plot is to understand this aspect of increasing the confinement is to plot the dispersion relation of let's say cavity frequency in some scale unit, cavity frequency divided by plasma frequency, and momentum divided, let's say, times, let's say, we rescale it with the length scales typical of the plasma, which is given by C over omega p. Okay, so if we do so, actually we capture the surface plasmon dispersion relation as a function of temperature. Okay.
Of course, the carrier concentration varies with temperature. It's a semiconductor, but other material properties also change. Like the screening length will also be changing with temperature.
Mm-hmm.
Does the change in the material properties manifest also here somehow?
Yes. So this is the non-local aspect that I will discuss. Exactly. That we start to see emerging when we really confine the photon, the screening length. So indeed, you start to see a deviation here. So okay, so these are compared, the experiments are compared with, let's say, parameter-free full wave simulation in a so-called local model that I will explain it in a minute. And this works very well, okay, up to a point that we start to see a slight departure, okay? So we wanted to figure out what's going on in the deep plasmonic regime. So this is a light line. So here really the modes are really confined in the deep plasmonic regime. I want to go further to see what does this deviation mean. So we went on to make very, very small cavities. These are our smallest cavities that still allow us to get a resonance that we can observe experimentally. So just for in terms of numbers, a terrace photon is typically 300 micron wavelength in free space. And this photon, typically around 1 terrace, will get confined to this 5.5 micron stripe, 200 nanometer, let's say, dielectric thickness, and the plasmonic material. So it's really, really small cavities. Actually, we've made also 2D cavities. And we in this type of system, we can basically squeeze the terrace photon in terms of volume to 10 million times smaller that we can get in free space. So there's really the nice thing of plasmonics that you can really confine. Okay. So what we see here is a similar plot as before. So we have the reflectivity as a function of frequency. We see the cavity resonance here. So this is the photon resonating here. Now, when we cool down, we observe basically the disappearance of this resonance as a function of temperature. Okay. If we do the same plot as I did before, so in scale unit, okay, cavity frequency momentum. So this is the dispersion relation we're expecting for the surface plasmon or cavity resonance, okay, in a local model. Okay. And we see now a complete departure of experimental point compared to this. Okay. This is the range I previously shown in the previous slide. So now you see that we are even more deeper into this plasmonic regime. So this departure, actually, we say it comes from the onset of non-local light matter interaction regime between the terrace photons. So we have squeezed so much our terrace photons, then they start to have non-local interaction with electron gas. Makes sense because, I mean, in a local model, this let's say dispersion would just saturate at infinity. It would mean that you can squeeze a photon to a point. Okay. Of course, it cannot be possible. At some point, this photon will start to see other length scale in your electron gas. And this is when you will start to manifest non-local phenomena. So this interaction between, let's say, non-locality in photonics or plasmonics is kind of a still challenging and open problem. So this is a recent review on the topic, a roadmap, let's say, what is the status of the field, or to describe the interaction of electromagnetic wave with, let's say, photonic system, which can show some non-local properties. So let's say, why is the problem complicated? Because, okay, first you need a good description of your, let's say, response of the electron gas. So here, for example, is the permittivity. So first you have different permittivities, whether they are transverse or longitudinal. Okay, so you need an accurate description, an accurate description of interaction with photon. The problem when you have finite photonic system is that, of course, even if you know very well the bulk response of your system, the surface response is different. That has one complexity to the problem. These waves, when they are transverse magnetic, they probe simultaneously in a complex way, longitudinal and transverse. So all these things mix a bit together, and this makes the problem difficult to tackle theoretically. So there have been different approaches. I just mentioned a few. I'm not really a specialist of all these approaches, but typically people have described. So what they want to, yes?
Well, I mean, naively, can't I just, as a first attempt, calculate just some high temperature equivalent of like a Linhart function? Like what we have for a degenerate electron gas?
Yes.
Yeah.
So they do actually, if you get the Linhart function, it can be complicated because you have logs in there. Right. So actually they do the first leading order correction to the local response, which is basically when you take the first spatial derivative. So they call it the hydrodynamic Drude model, for example. This is just the leading correction. So that allows you to have a momentum dependence into your permittivity, which is basically linear in momentum.
Does that work?
It works. Yeah, it works to some extent. It works to some extent. I will show you with our experiment, there are some limits, but it works for most of the features we observe. So hydrodynamic Drude model, we will make let's say, so we'll take the spatial derivative. There will be a beta parameter, which is directly related to the Fermi velocity of the electron gas. Let's say this gives you kind of an inductive response. So people have generalized this a little bit. You can, I think, derive this from this with a length scale here, which again have the beta, but they add an imaginary part to kind of describe diffusion, something which is damped to account for let's say dissipation in the system. Let's say another formulation that has been used quite a lot is Fableman D parameter, which are basically how to surface response function, and then other attempts also with transformation optics. So I will not go into the details. So if you're interested, you can see that. To come back to your point, so these are like hydrodynamic model that takes the leading correction in the momentum. That works to some extent, but you can imagine that if you really start to squeeze too much your electromagnetic field, you start to probe also higher momenta. And eventually also you will reach a moment where you cannot describe this in terms of collective dynamics, but you will have single particle excitation, electron hole continuum, and you will have breakdown of this description. And this leads typically to Landau damping. Okay. So in our system, we didn't develop any model. We just took one on the market, which is this one. So it is supplemented with boundary recognition and everything. Okay, so this one basically tells you that, as you mentioned, typically in this system, on the surface, the longitudinal electromagnetic field cannot change abruptly on the surface, okay? As it is considered in local models. So you have charges appearing in an infinitely thin layer on the material to screen the electromagnetic field, but actually they are smeared over a certain length, which is the charge screening depth, okay? Which depend on the Fermi velocity divided by plasma frequency. So we took a model actually, that simulates this and simulate this in a let's say, allows you to use local, let's say, to make a local simulation of a non-local problem. It's a mapping. And this works, so there is a single adjustable parameter that is the Fermi velocity, which is the new quantity in this problem, or screening depth if you want, it's the same. So this is the experiment, this is what we obtain in the local model. So we see this is now 1 minus the reflectivity, so absorption. This is a peak here, almost doesn't move. In experiment, it blue shifts. And in this, with this model, we're able to not only explain the blue shift, but also fit this blue shift to extract the Fermi velocity, or in other words, the screening depths. And this is reported here. So the screening depth we extract now as a function of temperature. So this is local electromagnetism when this depth is 0. And this is what you expect in this classical, let's say, not quantum, but classical electron gas, which is this double island, okay? And it fits okay. Let's say. I think we should do better in the future.
How degenerate are the electrons at these?
Not at all degenerate.
Not
Classical gas, 10 to the 16 room temperature, or let's say almost room temperature, very dilute. Let's say inter-electron distance of the order of 50 to 200 nanometer. To be a lot of unit cells. Okay. Okay, one thing which is not in this model and that we do see in experiment is when we squeeze too much, we have a disappearance completely of this resonance. And let's say this is because we have more dissipation than we expect, okay, from the simulation, and this can be attributed to the Landau damping. So in this regime where the plasmon actually decays into electron hole pairs, cross the electron hole continuum, or sense, let's say, the dissipation due to the electron hole continuum. So overall, this tells you that we are like the resonance disappears here, and this signals basically the end of the concept of the plasmon, okay, as a collective excitation because it decays. Ultimate limit for plasmonic confinement. Okay. I think I'm running out of time, so I want to show you a little bit the second part. Is it okay? So this was near equilibrium. Now I go back to my far from equilibrium phenomena I wanted to say. So we took our favorite metamaterial, our periodic array of cavities, which is spatially structured, and now we send a multi-cycle terahertz pulse resonant with the cavity. Okay, so this is a pump field, this is a pretty intense field, and then we probe the dynamics of the cavity with a broadband terahertz pulse, and we delay this time to probe as a function of time when the system is driven, how does it behave? Okay? So we are pumping this mode, which is the fundamental cavity mode I mentioned before. This is again the absorption of the mode, and we are pumping here. This is the Fourier transform of the drive. Okay, just below. So these are the experimental results. Here what you see is the time. So this is our pump pulse. This is a multi-cycle terahertz pump pulse, quasi-periodic, let's say. Okay. And this is the reflectivity of the metamaterial as a function of time, and this is the phase. Okay. So the phase, the cavity resonance, you always have a phase jump. So then you can track where is the zero here. It tells you roughly where the frequency of the cavity is located. Okay, so the pump pulse arrives, it detunes to the red the cavity, and then goes back to, let's say, equilibrium. Now, what's more interesting is when you zoom in this region in the vicinity of the peak field, you can see that, so this is the pump pulse, you can see that actually the cavity now, the cavity parameter, so frequency or contrast are modulated strongly, let's say, on the time scale of the cycle of the field itself. Okay, so these are the ultra fast modulation I was talking about. It's not just following the envelope of the field; it's just field driven. Okay, so every time you have a like electric field, the cavity is basically modulated in time. Okay, both in the amplitude and in the phase. Okay. If we look more carefully, we see that actually there are two modulation, 1 and 2 per cycle. Okay, so the cavity we say drive the system at omega, and the modulation is at 2 omega. Okay, so the way we interpret that is as follows. So we go back to what we know, the bulk plasma frequency. Okay, and now what we are modulating is not this, because we cannot like modulate the number of carriers like that fast. But what we modulate is the effective mass of the carrier inside the system as a function of time. And this modulates the plasma frequency in time, which again is locked to the cavity frequency. So this is how we can actually bring the modulation to the cavity frequency. Okay. Okay, so we developed a model about this. Let's say as simple as we could. So let's say we consider this plasmonic mode that we are driving, okay, as in terms of the collective variable, which can be the charge that pile up on the surface of the plasmonic mode here, and let's say the currents. And so you can describe this, let's say, as a LC oscillator, okay, with a capacitance and an inductance. And what we are modulating here is a kinetic inductance. So one important aspect of surface plasmon is that the energy of this mode actually goes at the same time in the electromagnetic energy, but also the kinetic energy of the carriers. Okay, this is what is, let's say, important for surface plasmon. And so this kinetic energy here, let's say, represented by the kinetic inductance is what we modulate and is directly linked to the effective mass of the carrier. Okay. Okay, so maybe I skip a little bit this detail, we quantize this. Now let me show you the comparison between experiment and model. So compares well. So what we did is, okay, we take this model, but on top of just like having the Hamiltonian, okay, we have, of course, dissipation in systems. So we had dissipation. And importantly, we want to compare one-to-one to the experiment. So in experiment, we are measuring the reflection coefficient, okay? So we need input-output coupling formalism. So how does the light goes to the cavity, gets modulated, comes out, okay? Which allows us to compare directly. So this model has a single adjustable parameter. We can calculate everything or measure everything experimentally. The only single adjustable parameter is basically the amplitude of the effect, okay? So we want to know what is the amplitude of the effect to be able to know if these modulations are strong, not strong, etc. Okay, so what we get from this comparison is a modulation. So this parameter, maybe I should have introduced quickly, okay, is basically the modulation parameter that appears to modulate the bare cavity resonance frequency, okay? So this tells you what is the strength of the modulation relatively to the cavity frequency, okay? So this modulation parameter, the relative modulation of the cavity frequency, is of the order of 20%, which in this system, if you convert to effective mass modulation, it's 80%, okay? So we have the ultra-fast modulation, okay? We have, in principle, ultra-strong modulation here. It's not 100%, but it's of the order of 40–50%, okay? So in principle, we are in this regime of the plasmonic time crystal, okay? At least from what I said at the beginning. Now you may wonder, okay, are there some signatures, spectroscopic signature of photonic time crystal effect here, and how do they manifest actually? Which is something new that we discovered actually, how to probe the photonic time crystal. So this is what I call spectroscopy of photonic time crystal. So here, this is a reflection coefficient that we measure experimentally, okay? There is a background, plasmonic background. Because the system is modulated, we just decompose it in Fourier harmonics. Okay, so we have the zero order Fourier harmonics, in other words, the average reflectivity, and the first order Floquet band, so the one that leads to the modulation. Okay. So the zero order resonant contribution is basically due to the cavity resonance that is there. So we see basically resonance. Okay. I show here the real and imaginary part of the resonance. And if we look at the Floquet sideband, so the first order, the positive Floquet sideband, the negative Floquet sideband, okay, what does this Floquet sideband tell you? They tell you actually, let's say, process in which photons are converting by one, or let's say two times the modulation of the, let's say, are up converted or down converted by the drive. Okay, this is what they prove. These Floquet cycles. So what you see here, they are compared to the let's say the zero order resonance. What you see here is something very peculiar. First of all, the resonance have a different shape that we expect. It's not like the standard resonance that we expect. Okay, it has a shape which has negative wing and much faster decay here. So this is not a first order resonance, or let's say standard resonance, it's a second order resonance. I will come to this just a bit later. Second order pole, okay? And they are strongly single-sided. This tells you something very important that we can understand in the following way. So the way to understand what we do is, okay, we have a cavity resonance to start with, okay? And typically this corresponds to two, let's say, poles. When you, let's say, you have the cavity resonance, a given frequency. In nonlinear optics, you always consider positive and negative frequency when you do frequency conversion. Okay. So a single resonance, actually, you can describe it in your, let's say, complex plane as two poles, one with positive real part, which is the central frequency, with negative real part, and the imaginary part, which is just the line width of your resonance. Same thing. Okay. what we do with our drive is that we create this flow-K replica that I talked about at the beginning. So we take these poles and we shift it close to the original pole of the cavity resonance. Close, but not directly on it, okay? And in this regime, actually, photon can come into one side of the cavity, gets scattered multiple times, okay, and can go out either from the same side or from the other side. So from the same side, this is what this probes. And when the photons come here and get multiply scattered and comes out there, for example, this is what this probes, okay, the flow-K sidebands. Okay, so the PTC goes like this. When you increase the drive strength, these two poles, they will coalesce together because of the strength of the drive. You can think about two-level system in which we crank up the drive. Typically it will, let's say you will have level repulsion, but in this system you have level attraction, okay? So they will coalesce and the imaginary part after this coalescence will be different for the two modes, okay? And this is where you enter the PTC regime, okay? So our colleague from the group of Markowski did a nice flow-K theory about this, which basically reproduce all these experimental features that we see. Let's say this single-sidedness for this resonant pathway for conversion. And most importantly, that gives us a guide actually to extract experimentally where these two poles are located. Okay, so the flow-K eigenmode of the system. One thing which I've mentioned is that you can show that actually first order flow-K sidebands have this functional form, and this is why actually you've got a second order resonance here with the first order resonance. Okay, so we take this theory and basically we use to fill these poles, and this is what we get. Okay, this is the experiment. So this is the real part of the pole, and this is the imaginary part of the pole as a function of time. So we treat the drive as a drive with slow varying amplitude compared to the fast modulation. So we do Fourier transform at every time to know exactly where the poles are located, to extract the location of the pole. So what we see is basically that the real part goes to the same value. So it's a pole coalescence here because the imaginary part is the same. After which basically we have same real part and different imaginary part. Okay. So this is where we enter the photonic time crystal regime here. And this is what our model predict, let's say, in the for the regime of parameter we are looking at. This input experimental parameter.
Can you remind me what is this parameter eta 0?
Eta 0 is the strength of the drive. It's the amplitude of the drive. So here we are considering, okay, in experiment we do something with a drive that is a pulse. So goes from 0, goes up to a certain value, goes down, okay? And we consider the system to be kind of adiabatic, okay, because it's slow, varying, okay? And we compare this to a model which considers that you have, let's say, you drive the system for infinite time, okay? So this is, you cannot compare one-to-one really in this respect, but it's not so bad. It's a slow varying amplitude. Then you consider that the system actually, you have the fast modulation, but equilibrates while you're driving. And so what we observe here is that in the PTC regime, there is one imaginary part of the poles that goes down, and we decrease the plasmonic loss typically by 50%, which is also a big number, okay? And it's quite encouraging because plasmonics is really good, for example, to squeeze photon way below diffraction limit. The price to pay is dissipation. This is why sometimes we don't want to use plasmonic system. So if we can develop systems which are at the same time able to squeeze photon and have little dissipation, then this is good. And then I will just finish because it's the last thing I want to mention. So what we are working on at the moment is to get the last remaining 50% in which you will have this prediction of lasing. Okay, so if you manage to decrease the loss you have, okay, if this, let's say, imaginary part cross 0, then you have gain into the system and exponential amplification until the point you have other types of nonlinearities in the system. So if I put, this is theoretical here, but if I put this result into the broader, let's say, range of the parameters of this platform. So here we have the scaled, let's say, drive frequency compared to the resonance frequency of the cavity. And here, this is the scaled, let's say, drive amplitude, okay? And the PTC regime is what you see in color, okay? In red color here, what is in the white area is just a modulated system. System which is modulated, but in which you have not entered the PTC phase where you have this mode coalescence. Okay, so in this phase diagram or in this stability diagram, here you start to see in the dashed line reflectivity going above 1. Okay, and here you have the lasing threshold. Lasing threshold is when the gain, which is this quantity, actually overcome the losses we see in our systems. Okay. So our experiment is located here. So actually we start from here, we go up to here, PTC regime, then we come back. And so now we are working to trying to access this regime. And the way we plan to do that is that our cavity were not maybe do not have the best design for the moment. Okay. So one way we can improve that is to actually make the cavities bit smaller to increase this kinetic inductance, which is the one we are actually modulating. In the cavities we were looking at here, there was a part of the cavities that had the Okay, conclusion and prospects. So this plasmonic, let's say, metamaterial platform, we have many parameters and knobs actually to design it, either through spatial structuring. You can explore like deep sub-wavelength regime of the light matter interaction with the emergence of non-local magnetic field in the system. Something that I didn't talk about, but if you now put a magnetic field either out of plane or in plane, you have interesting effect due to the Lorentz force on these carriers. So we showed that actually we can kind of design so-called chiral cavities, which breaks basically let's say symmetry between left and right circular polarized photon in the system. And now we have the knob of time. So then we can of course combine at one point all these things to engineer these new emergent properties. Okay, and I will finish by thanking all the people who contributed to the different works and you for your attention.
In view of time, let's have one quick question, if there is any. Please.
Yeah, thanks. Very nice talk. About the kind of near equilibrium part where you were looking at the non-local dielectric function. I mean, that's an interesting quantity intrinsically, right, of the plasmonic material. So do you think one could try to do something different for the plasmonic material itself, and to learn about different non-local dielectric functions? Like how much, I understand.
Yes, you could. I think people are starting to look now at making, let's say, not so. This plasmonic is coming from free electrons, don't gas.
Right.
But then you can look at phonon polaritons, and you can build out also very small cavities from surface phonon polaritons, because let's say an infrared phonon has a Restralen band, again, like an opacity band, so you can build, you have this surface phonon polaritons, and then you can also explore non-locality, let's say, of the phonon branch. So now you start to access a high momentum inside your brane zone, or let's say rather high momentum into your brane zone of the surface of the phonon themselves. So you could try.
Could you use a 2D material, actually, do you think, or is that?
Yes. A lot of people are actually very interested in plasmonic 2D material because they confine even more, I think. They confine the field even more because of the atomically thin depths of the material. So plasmon can be even more confined. Yeah. And they do see non-local physics of the electron gases.
I see. I could imagine,
graphene
exactly. Yeah, by graphene, the non-local screening will look very different.
Yeah. This non-local physics is not just in the system; it's in its 2D material, 2D plasmonics.
Okay, thanks, Yannis again. We